afternoon, everyone. So today we are going to discuss pointing vector and pointing theorem. Okay, so in which we will see the derivation of this pointing vector and what is pointing theorem. Okay, so this is generally give an idea how power flow is there from transmitter end to the receiver end. Okay, so how much power flow is there? Okay, so it gives important information between for this electromagnetic wave which is traveling from transmitter to receiver. Okay, so suppose there is a transmitter and there is a receiver, and the power energy or power can be transmitted from one point to the another point. So from transmitter to receiver by means of this electromagnetic waves. Okay. So now we will see how much power is transmitted from this transmitter to receiver. Okay. So we can find the rate of such energy transported from one point to another point by using Maxwell's equation. Okay, so this is applicable for time varying field only. Okay, and suppose we assume a surface. So this is in a medium, so this will travel in a medium. Okay, so suppose we assume a surface S. Okay. So how much power is flowing to this surface? We can find how much power is flowing to this surface. We can calculate using Maxwell's equation for time varying fields. Okay. So this is given by J.H. Poynting. That's why it is known as Poynting theorem. Okay. In 1884. To this surface. We can locate using So let us consider a charged particle Q moving with velocity v in the region where there is time varying electromagnetic field. Okay, so at any instant the force experienced by the charge is given by new charge F is equal to Q E plus V cross V. Okay, so this electrical intensity is magnetic field and this charge is moving with velocity v. Okay, so where E and V are time varying fields, electrical and magnetic time varying fields. Okay, time varying electrical intensity and magnetic flux density respectively. So when charge travel a distance dl, okay, so let's suppose this charge is here and is travel the distance vector dl and time dt. Okay, so in time I am taken to travel this length dl is dt. Okay, so under the influence of this force F, which is given by Lorentz force. So work done by the force on the charged particle will be given by, you know, that dw is equal to F dot dl. So this will be equal to QE plus V cross B dot D. Okay, so this will be the work done in moving a point charge from this point distance dl in time period of dt, small time period dt. Okay, so now so also power will be equal to dw divided by dt. Substitute the value of dw, so this will be equal to QE V cross B dot dl upon dt. Okay, so we can write like this. And what is dl by dt? So this is distance by time. It gives you vector b. Okay, so power will become q e v cross b dot product vector. So this can be written as 2e dot product b plus v cross b dot product. Okay. So we can write like this. So where P is the power supplied by the field. Okay, and we know that P cross B is the vector identity dot product B is equal to 0. Okay, so this value is equal to 0. So power supplied E will be equal to Q E cross B. Okay. So from this equation it is evident that time varying magnetic field does not supply any energy to the charged particle. Okay. So it is applicable only for this time varying magnetic field. Okay, so the power supplied by time varying magnetic field is equal to 0 to this charged particle. Only the electric field intensity supply power to the charged particle. It is as it moves through the region. Okay, so let us consider the volume distribution of the charge with charge density rho v moving with an average velocity of v. Okay, so the power supplied by the field on this small charge will be given by. Okay, we know that Q is equal to rho v into dv. So this v is for velocity and this small v is for volume. Okay, so this dv can be written as small power will be equal to rho v into dv. So Q is replaced by rho v dv E dot vector. Okay, like this. And you also know that J, vector J is equal to rho v into velocity v. Okay, so current density J is equal to rho v times into volume. Okay, so this will be equal to Vp. So this rho v and v can be written as J dot E into V. Okay, so the power density P is defined as power per unit volume. So small p is equal to dP upon dV, which is equal to J dot E. So this is the energy density. Okay, sorry, this is power density. So dP upon dV is equal to J. So one thing is clear, in moving a point charge, so power supplied by the field by varying time varying magnetic field is zero. Okay, so only electric field intensity is there which provide power to this moving charge particle Q. Okay, to obtain a similar expression for the static field on the basis of conservation of energy, we have to now, so this is true for time varying fields. Okay, so we use the relation we use the relationship between first, energy stored in time varying electric field, second, energy stored in a time varying magnetic field, and third, instantaneous power flow out or into the given region. Okay, so we will use the Maxwell's equation to find this Poynting vector. Okay. So what we will do? So from Maxwell's equation, we will derive Poynting theorem. From Maxwell's equation, or we can derive from Ampere's law, modified Ampere's law. We know that curl of H is equal to J plus del D by. Okay, so this is Maxwell's equation in point form, which is derived from Ampere's law. Okay, for time varying magnetic field, it is applicable for time varying magnetic field only. Okay, so now we will multiply so dot product by vector E. Vector E dot product term of H is equal to JE plus E del D by. Okay, so we have substituted this dot product this above equation with vector E. So now for any vector field A and B, for any vector field A and B, okay, so here E and H are two vector fields. So divergence of curl A cross B is equal to B curl of A minus A curl of B. Okay. So this is our vector identity for any vector field AB. Okay. So if we replace by A by E and B by H, so we will have E cross H will be equal to H curl of E minus E curl of H. Okay. And what we want? We want this E curl of H. So this is E curl of H. So you can written as vector E curl of H is equal to vector H curl of E minus divergence E cross H. Okay. So now we will substitute this value here. So vector H curl of E minus divergence of E cross H is equal to JE plus E dot divided by this. Okay. Or on rearranging it, we can write as okay. So here this curl of E. So by Maxwell's equation, which is derived from this Faraday's law, the curl of E is equal to minus del D by for time varying fields. So substitute here the value of curl of E. So this will be minus H del D by dt minus curl of the divergence of E cross H is equal to J dot E plus E del D by, or it can be written as J dot E plus E del D by dt. This will be H del D by dt plus divergence of E cross is equal to 0. So this equation is known as point or differential form of Poynting's theorem. Okay. So this above equation is point or differential form of Poynting's theorem. Okay. So this equation, in fact, a statement of the law of conservation of energy. The vector E cross H is vector E cross H. This vector, okay, has units of power density. Okay, so that is power density is unit. of power density is watt per meter square upon watt per meter square, and is called as Poynting vector. Okay, so this is Poynting vector. Okay. So the Poynting vector is the instantaneous flow of the power per unit area. Okay, and the direction of the power is normal to the plane containing vector E and vector H. And find it, both this vector E and vector H are time varying magnetic field. Okay, so the Poynting vector can be denoted by vector S or vector P. Okay, so some for those vector S and some maybe S vector P. So vector P is equal to E cross H. So this is Poynting vector. Okay, so if let's suppose if E is in the X direction, okay, and H is in A Y direction. Okay, so let's suppose E is in X direction and H is in Y direction. So the vector P, Poynting vector, will be in Z direction. Okay, so this will be always normal to the plane of E and H. Okay, we do this Watt's code. So now for time varying fields in linear, homogeneous and isotropic medium. So we are assuming that the medium to which this electromagnetic field traveling is homogeneous, linear and isotropic. So for such medium, let the J will be equal to sigma E D is equal to epsilon E and B is equal to mu into H. For such medium, value of J will be equal to J sigma E, D is equal to epsilon E and B is equal to mu into H. Okay, so we can replace equation, we can rewrite. So this will be equal to sigma E dash plus vector E del epsilon E by del T plus vector H del mu H by del T plus divergence of E cross H, which is a complete vector. Okay. Now this term E epsilon E del T, okay, it can written as epsilon by 2 del E square. So this will be magnitude square. Okay, so differentiation of E square will be 2 into E. So here it is only E into del E by dt. Okay, so differentiation will be this thing. Similarly, we can write for H. So this will be mu into H del by dt. So this will be mu by 2 del H square. So this is magnitude. Okay. This will be magnitude. So we can write this equation as sigma E square. So no need to let it be JE on this. Okay. Plus this will be half epsilon by 2 del V square by del T plus mu by 2 del H square by del T is equal to minus divergence of E cross S. So here, this term mu by 2 del H square by del T represent the rate of change of energy density in magnetic field. Okay, in magnetic field, we have seen this when we are studying the magnetic field. Okay, and this term epsilon by 2 del E square by del T represent the rate of change of energy density in the electric field. Okay, so thus the instantaneous expression of energy density in magnetic field is this, and in electric field is this. Okay, so now this expression for energy density. So for time varying fields. Okay, so this is applicable to time varying fields, and also for those obtained from static fields. The only difference is that field is now varying in time. Okay, so now what we do, we will integrate this whole equation with a volume, small volume. So this will be J dot E dV plus integration volume epsilon by 2 del square by del T plus mu by 2 del H square by del T is equal to taking the volume integral on the both the side. Okay, now we will apply divergence theorem. Okay, here for this, so by divergence theorem, volume integral divergence of E cross H dV will be equal to surface integral E cross H dot X. Okay. So this can be written as this will be negative sign. So this can be written as negative surface integral E cross H ds is equal to volume integral J dot E dV plus volume integral epsilon by del E square by dv dv plus volume integral mu by 2 del H square. So this is integral form of Poynting's theorem. So this is integral form of the Poynting's theorem. This is Poynting's theorem. So this is the power flow coming out of a small surface. Okay, so this term is volume integral K dot dv. So in the in this class, so this term is equal to, so P is equal to J into E. So this integral represent power supplied to the charged particle by the field. Okay? So this is power supplied to the charged particle in the field. Okay? So we have seen again in this lecture. Okay. And so whenever charge flow in the direction of the electric field, so current will flow through this due to this flow of charge, and this will account for the loss. So this will also account for the ohmic loss. So this we get in form of heat. Okay. So external force is doing the work in making the charged particle moving against the field, which is the when the integral is negative. So the in conductive medium J is equal to sigma E, the term represents the power dissipation or the ohmic power loss. Okay? So this will represent ohmic power loss. Okay, and it also apart from this, it also gives the power when motor moves, okay, or a generator generating energy. Okay, so when electrical energy is converting from to mechanical energy, and mechanical energy is converting back to electrical energy. So it can also account for this volume integral J dot E. Okay, so when we give electrical energy, so it imparts torque to the motor and it gives mechanical energy and rotor starts moving. Or on the other hand, for generator, we give mechanical energy and the energy is given to the system. Okay, so not only it accounts ohmic laws, ohmic power laws, it also whenever there is a change in energy from electrical to mechanical or mechanical to electrical or the energy given by battery, etc. Okay, so this is, and then we come to this. So this is a physical interpretation of this Poynting theorem. Next is volume integral epsilon by 2 del E square by del T square dV. It is the rate of change of electrical energy. Okay, and if it is positive, so this will be rate of change of increase of electrical energy. Okay, and in electric, okay. In last term, is volume integral dV by 2 h square by del T into dV. So this will be the rate of change of stored mechanical energy. Rate of change of stored magnetic energy. Okay, so when integral is positive and external source is supplying energy to the magnetic field, which results in increase in the magnetic field. Okay, so this will be rate of change of increase of the stored magnetic energy. And when if integral is negative, so the magnetic energy being extracted from the magnetic energy is extracted from the magnetic field and causing field to decay. Okay, and this term is term that represent the rate of change of stored energy in an electric field. Okay. And this minus E cross H surface integral here can also be done as minus vector P dot ds. Okay, so this is Poynting vector. The negative side on the left hand this negative side of the left hand side of the equation indicates that the power net power flow must flow into the volume V in order to account the power dissipation in the region as heat, this only power loss, okay, plus increase in the energy stored in both electric and magnetic field. Okay, and for static field, okay, so I have said that it is only applicable for time varying field, and if you want to write equation for static field, so we will have, so these two are time varying fields. Okay, so only term which is independent of time is this one. Okay, so both are time varying fields. So E is time varying and H is time varying field here. Okay. So for static field, minus P dot ds that is equal to E cross H dot ds will be equal to volume integral J dot E. So there will be only ohmic power loss is there. So which implies is for static pole and it is for time varying. This one. Okay, so this states that the net power flowing through surface S into volume V is equal to the power dissipation in the volume. Okay, in any volume. So this represents the instantaneous power density vector associated with the electromagnetic fields at any given point. The integration over the Poynting vector, surface integral over Poynting vector over closed surface will give the net power flowing out of the surface. Okay. So it includes the ohmic loss, energy stored in electric field and energy stored in magnetic field. So we can conclude that the Poynting theorem states that the net power flowing out of any volume V is equal to the time rate of change in energy stored within the volume V plus the ohmic losses. Okay, so if it is flowing out of the given volume, so this will be decrease in the energy stored. Okay, so at that time, so this will be positive. So if it is going out, so we take it positive. This will be negative, and if it is negative, then there will be time rate of increase is energy stored within the volume V. Okay, so this is Poynting theorem. So we can draw the power balance in the electromagnetic field. We see consider diagram. So this is power balance in electromagnetic. Here, power is in here. Okay. So this gives the power inflow and out coming out of this field. Okay. So in between this we have three power. Okay. So first is this ohmic loss. So ohmic loss can be represented by a resistance. This is account for ohmic loss, ohmic power loss. Okay, then the rate of change of this electrical energy stored can be given by a parallel plate capacitor like this. Okay. And the rate of change of stored magnetic energy can be given by a current flowing through a conductor or by an inductor coil. J is flowing and B is in. So this is the physical interpretation of this Poynting theorem. So this is energy stored electrical energy this is stored magnetic energy. Okay. So from stored magnetic energy, we can show it by VH curve. So if we draw a curve between the so this area enclosed within this hysteresis loop. Okay. So this gives this to magnetic field. Okay. So this hysteresis loop shows the energy stored in magnetic field. So this area will represent the magnetic field. So we can find the average P average is equal to 1 upon P. We integrate this P the function of time into so the time period T. So this will be P average. This is a function of Z. Z. Or the total time average power crossing the surface. The total time average power crossing the surface S will be equal to crossing the surface S is given like P average is equal to integration over surface P average So, Poynting theorem gives an idea the net power flowing out of a given volume. Okay, so how much power it transferring from transmitter end to the receiving end through a small surface area. Okay, this is all about